Hi there, this is Professor McCormick, and I'm back with the third video in the series related to the product rule, the quotient rule, and the chain rule. This video is on the chain rule. So in the previous videos, you remember, if you've watched them, that we identified the two smaller functions that are multiplied or divided. When they are multiplied, we use the product rule, and when I had two smaller functions that were divided, I used the quotient rule. Here, rather than looking for just smaller functions that are multiplied or divided by each other, we are looking for inner and outer functions. So it's a slight change in what we're looking for here, and we can put these all together in the end. But let's take a look at the chain rule as it is and how I find an inner and an outer function. So here, if I look for an inner function, what I'm thinking of is what's the first thing I'm going to evaluate or do if I were to say find f of 1. So the first thing I would do is find this value right here for 2 times 1 squared minus 5 before I cube anything. So that's a hint. The first thing I do is my innermost function. So that means w equals 2x squared minus 5. And you'll note I'm using a w here just because we used a u and a v in the previous section. I wanted to keep it unique. As we move on to more complex functions down here, I'll start using u's and v's again, probably. But just so that you can see them here early on, you can see those innermost and outermost functions, and I'm going to define them as a w and a y when I just have one. Now my outermost function, the last thing that I do on this particular function before I find my answer is to cube that innermost function, so I'm going to have a w cubed. If I look at the second one, I have a 3x cubed plus 1 to the negative 2 power. That negative 2 does not bother me at all. The first thing I do if I were going to, let's say, evaluate at x equals 2 is put in a 3 times x, or times 2 to the third power plus 1. So that is my innermost expression or function. So I'm going to have a w is equal to 3x cubed plus 1. My outermost function, then, the last thing I do before I have my answer for g of 2 in this case or example, would be w to the negative 2, and that's going to work for any x value. I'm just using these numbers as an example. Let's say we look at a trig function here. Before I can evaluate that trig function, I'm going to have to evaluate whatever my x value is for 3x squared. So let's say I had a pi over 2, then I would want to do 3 times pi over 2 squared. So that's the first thing I do. So we're going to write that as our w, our innermost function, 3x squared, and our y is going to be the last thing we do in this case, so it's the tangent of w. So it's the next thing I do. In this case, it's also the last thing I do. Here, the very first thing that I do is going to be on this y one, is evaluate this exponent. Let's say I want to find y when x equals 0. Then I'm going to say that 2 minus 3 times 0 squared is equal to 2. And so my very innermost function is going to be that w is equal to 2 minus 3x squared. The only other thing I have to do then is evaluate that e term once I have the w. And so I'm going to have an e to the w. One of my favorite functions. All right, so let's take a look at how we can use this information with the chain rule to find our derivatives. So if you remember, right, the chain rule, if I have w, that's the inner function, and y is my outer function, then I can say that f of x is equal to y of w of x. So that's that composite function, all right? So you can notice there that w is my innermost function and y is my outermost function. Then my derivative of f is going to be just y prime, w prime, or the derivative of y times the derivative of w. So it's not too bad at all to try and figure that all out, right? Much simpler. There's not as much going back and forth, adding and subtracting. When you talk about a chain rule, it's all about multiplying. So you're thinking of it as just kind of a chain of derivatives, all right? And we'll see why we use that chain in just a moment. So here, if we look at that original function again, remember the first thing I'd evaluate would be my w is equal to 2x squared minus 5, right? My y I'm going to write over here just for ease, and I'm going to say that's equal to w cubed. It's the last thing I'm going to do, so I'm going to evaluate this w first, and I'm going to evaluate this y second. All right, so let's make a little table, kind of like what we had before. I'm going to find my derivative of y first. So my derivative of y is going to be equal to 3w squared. Well, that's great, and it's really easy, but I really don't want my answer in terms of w. I want it in terms of x's, because my original function over here is f of x. So what I'm going to do is I'm going to take this w term right here, and I'm going to put it, basically the value, the 2x squared minus 5, I'm going to sub it back in for w, so I'm going to have a y prime is equal to 3 times 2x squared minus 5 all squared, because that w was squared. Now if I want to find my derivative of w, then I'm going to have a 4x down here. All right, now that we have our derivatives, we're ready to find the derivative of f. So the derivative of f, here I am just going to multiply straight across. It's a chain, it's nice and straight, it just goes straight across those derivatives. So I'm going to have 3 times 2x squared minus 5 all squared, and then I'm going to multiply that by a 4x. All right, and I'm going to put that one in parentheses just so I know that. Now I can combine two terms here. I can combine my 3 and my 4x term, and I'll come out of there with a 12x times a 2x squared minus 5 all squared, and that's my answer. Okay, so the chain rule is not too bad at all. Let's take a look at the second one. If you remember my innermost function, the first thing that I would do if I was trying to evaluate it would be the 3x cubed plus 1, and that was written wrong over here on this side, so let's turn this into a cube. And then my outermost function is the y is equal to w to the negative 2. We already kind of talked about those ones. So let's separate these a little bit. There we are. I'm going to find my derivative of y, which is equal to negative 2, w to the negative 3. Remember, I multiply by my exponent. Don't lose that negative sign. And then I have w to the negative 2 minus 1. That gives me my negative 3. Again, I'm going to substitute in my w value that's right over here. Because I don't want my final answer in terms of w, I want it in terms of x. So I have negative 2 times 3x cubed plus 1 all to the negative 3 power now. This is my y prime, or my derivative of y. My derivative of w is going to be 9x squared. All right, now I'm ready to find my derivative and use the chain rule. So to use the chain rule, remember I'm going to go straight across here. So I'm going to have let's flip back to a color I want, a negative 2 times my 3x cubed plus 1 all to the negative 3 power times my 9x squared. Again, I can put this term and this term together. So I'm going to have a negative 18x squared times 3x cubed plus 1 to the negative 3. All right, this next one, let's change the order these are in and copy that down. So here I have the tangent of 3x squared. Remember we said our w, the innermost function, was that 3x squared. And my outermost function was equal to tangent of w. That's the last thing I do when I evaluate that function at some value, say x or pi or whatever. So I'm going to look at my derivative of y. Remember the derivative of tangent is secant squared w. So here, subbing back in for my w, because I don't want to carry around that w, my derivative of y is secant squared of 3x squared. If I look at my derivative of w, here we're back to my favorite 6x apparently. Alrighty, so if I want to find my derivative of h, I'm going to, again, let's use a different color. I'm going to go straight across here. I'm going to multiply these together in a nice chain. And I am going to have secant squared of 3x squared times my 6x. I'm going to pull that 6x out front so it doesn't get confusing. So I'm going to have a 6x secant squared of 3x squared. And I'm done. Let's look at that e function that we had. So again, remember my w, my innermost function was 2 minus 3x squared. My outermost function, the last thing I did before I was done, was y is equal to e to the w. So my derivative of y, the easiest derivative there is e to the w. So I'm going to write that in terms of x, it's e to the 2 minus 3x squared, and my derivative of w is going to be equal to a negative 6x. Gotta love those sixes. I can find my derivative of y, which is also dy dx, if we want to write it that way, which is equal to, now remember, I'm just going to chain right across the bottom with both my derivatives. So I'm going to have e to the 2 minus 3x squared all times a negative 6x. Make sure you put parentheses around that negative 6x. We're multiplying those. We're not subtracting that 6x. I can write it out front a little more clearly by writing negative 6x e to the 2 minus 3x squared. Okay? Marvelous. Now, notice that there are times when I have to use the chain rule more than once to find a derivative. And so I want to take a look at that and how we're going to write it. So we're going to start with the innermost function and we're going to move on out. Okay, so we'll get further and further out as we go. So let's say I have an f of x, which is equal to e to the 2x squared plus 3, all of that cubed. Now I have a lot going on here, but I'm immediately thinking about that chain rule, right? I'm seeing inner functions. I'm not seeing any multiplication or division here. So I'm not thinking product rule or quotient rule. So let's start with the very first thing that I do. The very first thing that I do here is if I was trying to find, let's say, f of 1 or f of 2 or whatever, I would put my 1 or my 2 in there and find 2 times whatever number it is squared plus 3. And so that's going to be, we'll call that my w still. So that's 2x squared plus 3. All right. The next thing I would do is I would cube that. So I have another function that's coming in there. And that function is kind of this function right here. Okay. It's whatever that is in there cubed. So I'm going to say that I have, we'll name it a u this time, is w cubed. All right. So now I've got two functions going on. I have one last one. I need to take all of that and you put it in the exponent and take e to that u. So my y function is going to be e to the u. See how they're kind of lined up in the order that I would do it. I would have done this one if I was evaluating first, this one second, and this one third and last. So let's take a look at my derivatives. I'm going to work back across from 3 down to 1. So I'm going to have a y, the derivative of y is equal to e to the u. I do not want that to stay in a u, so I'm going to say that's equal to e to the w cubed, which I don't want it in terms of w either, so my y prime is equal to e to the 2x squared plus 3, 7 in for my w, all cubed. You can see that one didn't actually change from my original function. Now my derivative of u is equal to 3w squared. Again, I don't want a w hanging out, so I'm going to say that my derivative of u is equal to 3 times 2x squared plus 3, all squared. Almost out of room there. I don't think I can get rid of that, but I'm going to move it over just a tad for us so we have some room here. All right, now let's take the derivative of our w, and that one's going to simply be the derivative of that function right up there, and it's going to be a 4x. And now we have all of our derivatives, so we can find the chain rule of this. We can use the chain rule to find the derivative of f. So I'm going to use that lighter purple color again so you can kind of see through it. I'm going to chain all the way across. See how I'm creating the chain to link these together? These are multiplications. So I'm going to have an e to the 2x squared plus 3 all cubed multiplied by my 3 times 2x squared plus 3 all squared, that's my u prime, all times my w prime, which is a 4x. All right, I have a couple terms I can put together here. Let's change back to yellow. I see this and this, the 3 here and the 4x there. We're multiplying across, so I'm going to multiply those two together. I'm going to get a 12x. I'm going to pop my 2x squared plus 3 squared out front, so I'm going to have a 2x squared plus 3 squared, and I'm going to throw that e to the 2x squared plus 3 cubed on the very end, and that's my answer. So it's really, really just that easy. Let's take a look at another example, because I have a lot of nice room here. So here I'm going to look at another nested function. Okay, my innermost thing, the first thing I'd do if I was trying to find, let's say, f of, let's find f of 1, would be to pop a 1 in right here. Okay, so that's the very first thing, is I would find 1 squared. So I'm going to say that means that my w is equal to x squared. All right, I'm going to make a little mark there so that we have a line across. The second thing that I would do here is I would then take the natural log of whatever my x squared is. So I'm going to make that my second function, u equals w. Oh, wait, what am I doing? U equals the natural log of w. Let's pick the right marker here. W. So I'm taking the natural log of that x squared term. And now let's give us a little bit more room here. We'll come all the way over here. I'm going to say the last thing that I would do, right, would be to take the tangent of this. In this particular case, that's the end of my chain of what I'm going to pop in there. So I have tangent of u. Let's take the derivatives. We're going to work backwards. Remember, I found this, I'd do it first. I found this, I'd do it second. I'd do this third if I was evaluating. So I'm going to work back this direction. I'm going to say y prime is equal to secant squared, because that's the derivative of tangent u. I'm going to sub back in. I'm going to say that means that my derivative of y is equal to secant squared of the natural log of w. I'm not done yet because I haven't gotten an x in this derivative. So my derivative of y is equal to secant squared, the natural log of x squared. And I'm done. There, I can nest some things around there. All right, now let's look for our derivative of u. So my derivative of u, remember the derivative of the natural log is 1 over the quantity inside, so 1 over w. In this case, I want that in terms of x, so I'm going to say my derivative of u is equal to 1 over x squared. Now my derivative of w is going to be 2x, and I'm ready to take my chain because I have the whole chain written right there. I have my derivative of f is equal to, and remember, I'm going to go straight across here. Let's see if I can get that to kind of go straight across there. You can see how straight I write, or don't. So I'm going to have a secant squared of the natural log of x squared. That's my first term. All times this 1 over x squared term, that's my u prime, all times a 2x. Okay, that's my w prime, or my derivative of w. Now you'll notice that we can take this pink, this term and put them together. And so I'm going to have a 2x over an x squared secant squared, natural log of x squared. It's a lot of things happening there. And I can reduce this. I have an x here, and I have one x down here I'm going to get rid of. So I'm going to have a 2 over x. Oops, that's not an x. X secant squared, and then natural log of x squared. And we're done. If you want to write the 2 and the secant squared together term there on the top in the numerator, feel free to do that. All right, you're more than welcome to do that. So you can see how we can chain this all together. So even if we have something super crazy going on, we can continue to chain out. All right. If you have any questions on this, let me know. I'm going to go ahead and do one more video that shows us using the product rule with the chain rule, and maybe one with a quotient rule with the chain rule, and it'll just be those examples, and we'll be good to go. Have a great day, and let me know if you need anything. Bye-bye.